we have some properties of logs that we're gonna want to go over. Log base b of x times y is log base b of x plus log base b of y. This is the product property of logs. And it's just if we have the log of two things multiply together, we add the logs. A logarithm is an exponent. When we have the exponent of two bases multiplied together, we add the exponents, we add the logarithms. That's where that comes from. It comes from our exponent rules. The log of two things multiplied together is the log of the first thing plus the log of the second thing. And what if we were talking base 10? The log of two things multiplied together is the log of the first plus the log of the second. What if we had natural log? Same deal. Doesn't matter what the base is. This property is always the same. The natural log of two things multiplied together. Natural log of the first plus natural log of the second. How do we use this? Let's say we had the log base 2 of 8x, and we want to write the logarithm as a sum. The log of two things multiplied together is the log of the first plus the log of the second. Simplify if possible. 2 to what power is 8? 3. A logarithm is an exponent. The exponent here would be 3. So we can use this property to simplify logarithms. What if we had the natural log of 5xy? Well, this property can be extended. This is 3 things multiplied together. So it's going to be 3 logs added together. It's the natural log of 5 times x times y. So that's the log of 5 plus the log of x plus the log of y. In this case, we were using the natural log. Similar property. The quotient property. Log base b of x over y, the log of two things being divided. It's the log of the first, the log of the top, minus the log of the bottom. So when we are dividing inside of the log, that would be subtracting the logs. Again, it comes from the exponent rule. When we're dividing two bases, we subtract the exponents. Couple examples here. How about the base 3 log of c over d? Well, that would be the base 3 log of c minus the base 3 log of d. What about the log? So that's the common log, base 10, of x over 1,000. That would be the log of x minus the log of 1,000. And this simplifies as the log of x minus 3. Because when we don't have a base written, it's base 10. And 10 to the third power is 1,000. The logarithm is an exponent. The exponent here would be 3. We also have a really cool power property of logs. If we're taking the log of something raised to a power, we can bring the power down front and multiply. So the log base b of x to the p, bring it down front and multiply. P times the log of b, the log base b of x. How would we use this? Well, let's say we have the natural log of the 5th root of x squared. We can write radical form in power form. Power over root. This would be the same as the log, the natural log of x to the 2/5. We can bring that 2/5 power down front and multiply. 2/5 natural log of x. Common log of x squared. Bring the power down front and multiply. 2 log x. Now, these 3 properties we've looked at aren't always just going to be there all at once or on their own. We can get them all at once. That's the point I'm trying to make. For instance, if we had the log of AB over C, we would add log of A plus log of B because of the multiplying on top. And then because we divide by C, we would subtract log of C. These properties can be used in either direction. We can use them to condense too. Let's say we were given log of A plus log of B minus log of C. First, make sure all the log bases are the same, and they are. Since we're just adding and subtracting, we can write it as a single log where we're multiplying or dividing. Log A plus log B means we multiply A times B. Subtracting log C means we divide by C. Looking at an example, log base 2 of z cubed over x, y to the 5th. Let's write this as a sum or difference of logarithms. This quotient means that we have log base 2 of z cubed minus the log base 2 of x, y to the 5th. Why did I leave this together? Why didn't I just make it plus right off the bat? Well, we would be subtracting the entire log, which means we're subtracting the entire addition. I wanted to point that out, that we need parentheses. And that minus would get distributed. So minus log base 2 of x minus log base 2 of y to the 5th. And again, not surprising because the x and the y to the 5th are both on the bottom. They're both being subtracted in the long run. Now we just need to take care of our powers. The z cubed, the 3 goes out front as multiplication. Minus log base 2 of x, minus, again here, the y to the 5th, the 5 comes out front as multiplication. Let's do another. The log of the square root of x plus y squared over 10. I'm sorry, this is a cube root. Log of the cube root of x plus y squared over 10. We can write this instead of as a cube root to the 1/3 power. X plus y squared over 10. We can take that 1/3 power and bring it out front as multiplication. We have division happening here. One third is going to be times this log, which means it's going to be 1/3 times this difference. Log x plus y squared minus log of 10. One third of log of x plus y squared. We can bring the 2 down front of this log. Log base 10 of 10, 10 to the first is 10, so this is all just 1. And finally, just multiplying it together, 1/3 times 2 is 2/3. Log of x plus y minus 1/3 times 1 minus 1/3. And we can't break up log of x plus y anymore because it's not log of xy. If it was log of xy multiplied, then we would make it a sum. But there's no log rule for the log of x plus y. We can go in the other direction. Let's say we had 3 log a minus 1/2 log b minus 1/2 log c. This would be the log of a cubed minus the log of b to the 1/2 minus the log of c to the 1/2 or the log of a cubed minus the log of the square root of b minus the log of the square root of c. So the log of a cubed over, because they're both subtracted, they both end up on the bottom, square root of b times square root of c square root times square root, we can combine. Log of a cubed over square root of bc. Next, I want to show an exponential equation and how we can solve that. Let's say we had something like 3 to the 2x minus 6 equals 81, where the x that we want to solve for is in the very top, in the exponent. Well, if we can get it so both sides are the base raised to a power, the same base raised to a power, which we can do here, because 81 is 3 to the 4th. This implies that the exponents are equal. 3 to this equals 3 to that, this equals that. I'm going to break that down in a little more detail when we're done. Add 6 to both sides. Divide both sides by 2. We get x equals 5. The reason this works is because we're allowed to take the log of any base of both sides. So the extra steps here that we don't need to show because it's implied are that we're taking the base 3 log of both sides Then the powers are coming down front as multiplication. The base 3 log of 3 is 1 because 3 to the first power is 3. So 2x minus 6 times 1 equals 4 times 1. Which gives us 2x minus 6 equals 4, which we solved to get x equals 5. So what's really happening is that we can take the log of both sides. And it doesn't matter what kind of log it is. Here we use the base 3 log because it helps us get rid of the base. But in general, we're allowed to take any log of both sides. So keeping that in mind, let's say we have 5 to the 5x plus 6 equals 4 to the 8x. And we're given the direction, use natural logs. What that's telling us is your first step is to take the natural log of both sides. ln of 5 to the 5x plus 6 equals ln of 4 to the 8x. Well, then what would we do? Well, we have powers inside our logs. The powers come out front as multiplication. 5x plus 6 times the natural log of 5 equals 8x times the natural log of 4. We want to get all of our x terms on one side, everything without an x on the other. We also need to get rid of the parentheses first so we can distribute the natural log of 5. 5x natural log of 5 plus 6 natural log of 5 equals 8x natural log of 4. I'm going to subtract 8x natural log of 4 from both sides. That got everything on the left. I'm going to keep the 5x natural log of 5. I'm going to keep the minus 8x natural log of 4. But I'm going to subtract the 6 natural log of 5. And you'll see why we're getting all the x's on one side in just a second. But this would leave 5x natural log of 5 minus 8x natural log of 4. Subtracting this over, so this equals negative 6 natural log of 5. Let me move this up. Give myself more room to work. Okay. Now, since we got everything with an x by itself on the left, that means everything has an x on the left. That means we can factor an x out, and we're left with 5 natural log of 5 minus 8 natural log of 4. And we can divide both sides by this factored piece, leaving us with just an x. Now, if you have a calculator with a natural log button, you can find the decimal approximation here. But this is what I'm looking for. X equals, and then everything written in terms of logs. The problem is we don't like that we have the negative. In fact, we would prefer that the top is positive. So I'm actually going to go ahead and uncircle this because we're not in final form yet. If this was a multiple choice test, you'd get this far and you'd realize, oh, that answer is not there. The negative can go on the top or the bottom. We're going to put it on the bottom. But we can't just write negative and the rest of it. The entire bottom has the negative. Top's positive though, so we're almost done. Distribute the negative. Negative 5 natural log of 5 plus 8 natural log of 4. Whoops. Let me write this up here, give myself more room. This is tough, but this is on the final exam. Okay. So I distributed the negative on the bottom. Plus 8 natural log 4. And now the bottom can be rewritten. Since it's negative plus this, we can switch the order of addition so that it's 8 natural log of 4 plus a negative, which is just minus 5 natural log of 5. We don't like starting with our negatives. And that is the final form. And in a calculator, this ends up being approximately 3.1732. But that's not what I'm looking for. I'm looking for the natural log form. X equals this in terms of natural log. Let's look at one more natural log, or one more logarithmic equation. Also on the final exam, a problem like this. Okay. Our strategy. In the last one, we wanted to get the x by itself, but it was in the exponent. We ended up taking natural logs of both sides to get rid of that. Here, the x is inside a logarithm. And since it's inside a base 3 logarithm, we want to end up getting log base 3 of x minus 5 by itself with everything else on the other side. And then we're going to raise both sides as powers of 3. That'll get rid of the log. That'll free up our x. You'll see, I promise. So first, let's go ahead and start working towards getting the log base 3 by itself. We're going to subtract 10 from both sides. That leaves us with -2 log base 3 of x minus 5 equals 8 minus 10 is -2. How lovely. We can divide both sides by -2, which gives us our log base 3 of x minus 5 by itself. -2 divided by -2 is 1. I'm going to move this up so I have more room to work. I'm going to raise both sides as power of base 3. Which is the reverse of what we did when the x was in the exponent. That's when we took logs of both sides. Now that we want to get rid of a log, we need to make both sides exponents. The base 3's cancel, leaving us with just x minus 5, no longer in an exponent. 3 to the first is 3. Add 5 to both sides, and we get x equals 8.